Hello my dear students. So again I am going to continue with the extra questions related to hydrostatic pressure. So in the previous chapters also I have been discussing some extra questions. So this is extra question 21. Weight of an object in air is 3 newtons. The upthrust exerted by the liquid is 2.5 Newton. So again here you can see the weight of the object is greater than the upthrust. So you all know what will happen to the object if you put it into, here it is the liquid. They haven't said what liquid that is. So if you put it into that liquid, it will sink in the liquid. That you all know. When weight is greater than upthrust, the object sinks in the liquid. First one, will the object sink or float completely immersed or float partially immersed in the liquid? So I just mentioned that it will sink in the liquid because upthrust is less than the weight of the object. So it will sink in the liquid. The second question is to briefly explain your answer. So here only we have to say an object will sink in a fluid if the upthrust is less than the weight of the object. So you all can remember students, we discussed an activity, actually we did the activity in the lab where we used different objects. One object floats partially immersed in water, the second object floats completely immersed in water, and the third object that completely or sinks in water. So we measured the weight of the objects in air and then we measured the weight of the object when it is either partially submerged and floating, completely submerged and floating, or sunk in water. Then from those observations we came to some conclusions. You all can remember that. When the upthrust exerted by the fluid to the object is equal to the weight of the object will float completely immersed in the liquid. If it is greater, that is upthrust is greater than the weight of the object, what happens? Then only the object gets pushed upwards. So then it will be partially floating, partially immersed and floating in the liquid. So again, when we say partially immersed, it can be like half immersed or it can be only a very small part of the object will be immersed in the fluid. That again depends on the fluid as well as the object. Then in this instance, the weight of the object is greater than the upthrust. Then of course there will be a force acting downwards, that is the apparent weight. So because of that, the object will sink in the fluid. So here of course it is the liquid. So an object will sink in a fluid if the upthrust is less than the weight of the object. So here we need to explain it a little bit further. In this, the weight is 3 Newton and the upthrust is 2.5 Newton. Therefore, the object will sink in the fluid. So if we write that, that gives an explanation. Otherwise you can compare and write also. Weight is 3 Newton which is greater than the upthrust 2.5 Newton. Therefore the object will sink in the fluid. So that is how we can explain this observation. With that students, I will move on to the next slide. Extra question 22. What is the instrument used to measure the density of liquids? You are familiar with the instrument. What is it? The hydrometer. So here the answer is hydrometer. How is the above instrument made to float vertically in the liquid? How is it made to float vertically? You can remember the structure of a hydrometer. You don't have to draw it, students. I'm just doing it here just to recall what we discussed. So there is the glass tube, then it is calibrated, and inside the bulb, what is there? There is either lead or mercury. So this is the glass tube with a bulb. Inside the bulb there is lead or mercury. So this lead or mercury, they are metals, they are heavy metals. So because of that, this particular hydrometer gets a certain weight. And this weight helps the hydrometer to float vertically. So there we have the glass tube and the calibration also. So the question is, how is the above instrument made to float vertically in the liquid? By having lead shells or mercury inside the bulb. This makes the hydrometer to float vertically. Because when we say vertically floating, all the weight is contained within a small space. Now this is a very small space. So because of that, the hydrometer remains vertical. I am sure you all can understand that, students. So with that, I'll move on to the next question. Extra question 23. Figure below shows the water levels in containers of different shapes connected to a PVC pipe. So here you can see the figure. I am sure, students, you all can remember this activity. We have discussed this in your lesson as well. What can you say about the pressure exerted by water at points A, B, C, D and E? So here you can see the setup, students. There is a PVC pipe here, a PVC tube. Different shapes are connected, tubes of various shapes or containers of various shapes. But all of them are connected to the PVC tube. So here what do you see? All the containers have the same water level, the water level. If you take the vertical height, if you take this vertical height up to this point, then it will be the same for all the containers. Vertical height is going to be the same. But you can see in all these containers, the volume of water that is there is different because the shape is different. So although the shape and the volume of liquid inside the containers are different, still they all have the same vertical height. So from that, we were able to understand that the pressure exerted by liquids depends on the height of the liquid column, not on the shape or the volume of the liquid, shape of the container or the volume of the liquid. So from this, what can you say about the pressure exerted by water at points A, B, C, D and E? At all these points, the pressure is equal. So that is what you can say from the activity. Pressure is equal at all the points A, B, C, D and E. So that is what we can say from this. Then the second question, What can you conclude from the above observation? So I told you all the conclusion before also. The pressure exerted by a liquid does not depend on the shape of the container or the volume of fluid that is present. It only depends on the vertical height of the liquid column. So here all the vertical heights are equal and the pressures are equal at all these points because this is the same water. In water along the same level, the pressure is the same, so that you all know. So from that we can say the pressure is same at points A, B, C and D and E. So the vertical height is the same. So pressure depends only on the vertical height, not the shape of the container and not the volume of the liquid. So that is what you can say from the above observation. What can you conclude from the above observation? Pressure exerted by a liquid column depends on the vertical height of the liquid column but not, or we can say, but does not depend on the shape of the container or the volume of the liquid. Volume of the liquid. That is the conclusion that you can get from this activity. Pressure exerted by a liquid column depends on the vertical height of the liquid column but does not depend on the shape of the container or the volume of the liquid. Is that clear to you all students? So with that, we will move on to the next question. Extra question 24. Diagram of a mercury barometer is given below. So here you can see the mercury barometer. You can see a glass vessel containing mercury. Then there is a glass tube with one end sealed and there is the region X that is above the mercury column. So you know here this is the mercury column. Then if we look at the questions, first one, what is the significance of X shown in the diagram? What is the significance of X, that is region X? The region X has to be a vacuum. It has to be empty space. There can't be anything. No air, no moisture, nothing. Then only you will have a mercury column. Why? Because the pressure exerted here is the atmospheric pressure. This is P atmosphere and that pressure is equal to the pressure at this point. It will be equal to the pressure exerted by the mercury column of this height only if there is nothing above it. When there is vacuum, then there is no pressure exerted by the region X. Then only we will have a proper mercury column. So that is the significance. What is the significance of X shown in the diagram? X is vacuum. This is required to have a mercury column inside the glass tube that exerts a pressure equal to the atmospheric pressure. So what will happen if there is air inside region X? That air will exert a certain amount of pressure. So if we need to balance this and this pressure, the mercury column will come down a little bit. So instead of 76 centimeter mercury at mean sea level, it will be less than 76 centimeter mercury. But how do we measure the atmospheric pressure? Using the height. So we will get a wrong reading. So we have to make sure that this region is vacuum so that you get the correct height of the mercury column that corresponds to the atmospheric pressure. You have to remember that, students. Then the next one. A group of students observed that the mercury column in the glass tube does not flow down. Explain the observation. Yes, that is a very good observation by a group of students. Now, if we try to understand that, you can see the mercury column here. This is the height. So, by the mercury column, there is a pressure exerted at this point that is equal to H rho G. That is why we use the height to denote the pressure. That same pressure at this point is equal to the pressure here, which is in turn is the atmospheric pressure. So, how is this mercury column held up like that? Because there is pressure exerted by the atmosphere on this surface. So, that pressure is transmitted through the mercury that pushes the mercury column into the glass tube. So, because there is a pressure acting here that is able to bear this weight of the mercury column. That's how it happens. Can you all understand that? So, here what I will do is, I will mark these as X and Y, or already X is taken. So, we will say A and B. So, pressure at point A and point B are equal because there is a pressure acting at point B that keeps the mercury column from falling down. So, that is what we need to explain here. So, a group of students observed that the mercury column in the glass tube does not flow down. Explain the observation. So, I can say there is atmospheric pressure acting at point A. This is equal to the pressure at point B because it's the same level. So, if I write it short like that, you all know what that means. This pressure at the same level of a liquid is the same. So, pressure at point A and B are same. So, here this pressure at point B holds the mercury column within the glass tube. So what will happen if the atmospheric pressure decreases? Then the pushing pressure will be less at point A as well as point B. So then the mercury column that was initially there cannot be held by that pressure. So the column will decrease, the height of the column will decrease. What happens if the atmospheric pressure increases? So there will be more pressure exerted at point A and B. So because of that, more mercury will enter into the tube and the height of the mercury column will increase. So that is how the mercury barometer functions. Pressure equal to the atmospheric pressure is exerted at point A and B, like shown in the diagram. So because of that pressure, the mercury column is held vertically like that. It doesn't flow down. Is that clear to you all, students? So here, if we are to look at the answer again, there is atmospheric pressure acting at point A. This is equal to the pressure at point B. Pressure at point B. That is same level. This pressure at point B holds the mercury column within the glass tube. So that is the observation by the students, and we have explained the observation as well. So I am sure even you all were able to explain this observation. With that, students, I will move on to the next question. Extra question 25. The diagram illustrates how three objects are submerged in water. So if we look at the objects, you can see A is partially submerged and floating, B fully submerged and floating, C is sunk in the liquid, or here it is water. C has sunk in water. Weight of object A is 15 Newton. What is the upthrust acting on the object? The weight of the object is 15 Newton. What is the upthrust acting on the object? It will be also 15 Newton. You all can remember, students, we did this activity in the lab also for an object that is partially or fully submerged in a liquid, and if it is floating, the weight will be equal to the upthrust. So here weight of the object A is 15 Newton. What is the upthrust acting on the object? 15 Newton. So here upthrust equals weight. So that is equal to 15 Newton. Students, you don't even have to write upthrust equals weight. You can directly write the answer. But here for you all to understand and remember more, so I am writing these additional information as well. So weight of the object is 15 Newton. What is the upthrust acting on the object? 15 Newton. Second one, weight of object B is 18 Newton. What is the upthrust acting on that object? So B is 18 Newton. What is the upthrust acting there? That is again 18 Newton. So here also both the objects A and B, they are floating in water. So obviously weight has to be equal to upthrust. For the first one it is 15 Newton, second one it is 18 Newton. So the next one, weight of object C is 20 Newton. Is the upthrust greater or less than the weight of the object? So C has sunk in water. So what happens to the upthrust? Upthrust is always less than the weight of the object. That is why the object sinks in water. So here weight of the object C is 20 Newton. Is the upthrust greater or less than the weight of the object? It is less than the weight of the object. Upthrust is less than the weight of the object. Is that clear, students? So with that, we will move on to the next slide. The fourth question here. Is the upthrust acting on the object equal or not equal to the weight of the object when it floats in the fluid while being fully submerged in it and floats while partially submerged in the fluid? Is the upthrust acting on the object equal or not equal to the weight of the object when it floats in the fluid while being fully submerged in it and floats while partially submerged in the fluid? So, those are the first two instances, A and B. In both instances, the upthrust is equal to the weight of the object. So, that is what you have to write. Upthrust equals weight. When an object floats partially or fully submerged in a fluid. So, that is the relationship. If the object is floating, the weight is equal to upthrust. If the object sinks in the liquid, the weight is greater than the upthrust. So, these are conclusions that we got from the activity. So, you all know to apply them here. With that, students, I will move on to the next one. Extra question 26. Diagram of a mercury barometer is given below. Why is mercury preferred over water to make the barometer? What is the pressure in S? Explain your answer. So, to do that, we will first look at the barometer. Here you can see the mercury is given to you inside a vessel. Then we have the glass tube. You can see here the glass tube is right towards the bottom of the container. And here you can see points X, Y are marked. The height between the surface of mercury inside the vessel and up to here it is 70 centimeters. This part is 6 centimeters. And the space, the vacuum is actually labeled as S. So, those are the information that we can get from the above. So, coming to the first question. Why is mercury preferred over water to make the barometer? We have discussed that before also. Why? If you use mercury, you need a tube that is about 1 meter in length. But if you use water, you will need a glass tube of almost 11 meters in height or length. So, that is difficult to use. That is why they prefer mercury over water. And what is the reason for that? The density of mercury is 13,600, whereas the density of water is only 1000. So, the density of mercury is very high. Because of that, we need a shorter mercury column. So, that is the reason. So, here we can say because the density of water is very less compared to mercury, we will need a very tall glass tube. In brackets, I will say greater than 10 meters to construct the barometer. This is not very practical. So, that is the reason why we choose mercury or why we use mercury over water. Then the next question. What is the pressure in S? Explain your answer. What is the pressure in S? The pressure is 0. Why? S is vacuum. There is nothing that can exert a pressure. Only matter exerts pressure. Solids, liquids and gases. So, here there is no matter, there is only vacuum. So there is no pressure. So pressure is 0. Pressure in S equals 0, or you can just write it as 0. Explain your answer. S is vacuum. So there is no matter, that is solids, or gases, to exert pressure. And as we have already discussed in another question, you all know it should be vacuum. Then only the mercury column will be there. Otherwise, we will not get the correct reading for the mercury column. Because if there is air or something else, that will also exert a pressure that can push the mercury column down. So the height will be different from the real height. So that is the reason it has to be a vacuum, and because of that the pressure exerted is 0. With that, students, I'll move on to the next part of the question. Compare the pressure at points X and Y. At points X and Y, what is the pressure? At point X, the pressure is less. Point Y, pressure is more. Why? Because when you take point X, this is the height of the column, and point Y, it is 70 centimeters. That is greater. So because of that, pressure at point X is less than the pressure at point Y. Compare the pressure at point X and Y. I will write it as Px and Py. So Px is less than Py. That is how we can compare, or you can write it in your own words, or you can say pressure at point X is less than the pressure at point Y. So that is the answer. So here, what is the atmospheric pressure indicated by the barometer? That is the next question. Now here, students, what do you all think? There are two values given. This part is 70 centimeters. This part is 6 centimeters. So total is 76. Normally, we are used to the atmospheric pressure at mean sea level being equal to 76 centimeter mercury. Is that correct here? No. You all can remember, students, when we measure the height of the mercury column, it is the difference between this point where it is along the level of the mercury inside the vessel. The height is from that point up to the top of the mercury column. So that height has been given to you as 70 centimeters. So that is what we need to consider as the height of the mercury column for the pressure exerted by the atmosphere, or that is given as the atmospheric pressure. So here the question is, what is the atmospheric pressure indicated by the barometer? So that is 70 centimeter mercury. So you have to remember, students, usually it is at the mean sea level. The height of the mercury column is 76 centimeter mercury. But here, as you can see, the column has been, the glass tube has been pushed down right to the bottom. We don't consider that part that is below the mercury level, only above the mercury level in the vessel. So that is 70 centimeter mercury. Is that clear to you? So then we will move on to the next slide. Calculate the atmospheric pressure in Pascal. So here we need to calculate the atmospheric pressure in Pascals. You know the equation, P equals H rho G here students, if we substitute the values, H is 70 centimeters. Can we use it as 70 centimeters? No. We need to convert it to meters. So, we need to divide it by 100. Then, the density of mercury is 13,600. 13,600 and gravitational acceleration is 10. If we do the calculation there. So, it is equal to 7 into 13,600. That will be equal to 0.0259. That in Pascal. 95,200 Pascal. That is the pressure exerted by the mercury column. So, that is the pressure that is shown by the mercury barometer. We will look at the next one. Is the barometer kept at mean sea level? Explain your answer. We have discussed that before also. If it was at the mean sea level, what would be the height of the mercury column? It is 76 centimeter mercury. So, here it is less than 76 centimeter mercury, 70 centimeter mercury. So, that means the barometer has to be at a higher elevation. So, that is what you need to write here and explain. Is the barometer kept at mean sea level? No. So, why? If it was kept at mean sea level, the height of mercury column should be 76 centimeters. But in the above it is only 70 centimeters. Then the barometer should be at a higher elevation than mean sea level. So, that is the explanation. You don't have to even really say that it is at a higher elevation. You can stop at the point where we say it is not equal to 76. It is less than 76. So, it can't be at the mean sea level. I am sure you all can understand that, students. So, with that, I will move on to the next question. So, extra question 27. A group of grade 10 students carried out the activity given below to demonstrate the Archimedes Principle. So, you are familiar with the Archimedes Principle, students. What is it? When an object is completely or fully submerged in a fluid, the upthrust exerted by the fluid is equal to the weight of the fluid that is displaced by the object. That is the Archimedes Principle. So, an object was immersed in water as shown below and the weight of the water displaced and the apparent weight were measured. So, here you can see there are three diagrams given. In instance X, you can see the object is half submerged in water. Then the reading is 50 Newton. There is water collected in the beaker. Then instance Y, you can see it's further immersed into water. So, the reading has decreased further 20 Newton and also you can see the two levels of water that has been displaced. Here there is more water displaced. And in Z, the third instance, you can see the Newton balance reading 0. That is when the object is completely submerged in water, and here the weight of water that has been displaced is given as 100 Newton. So those are the information that is given to us. From this activity, since we have done this activity in the lab, we got different values, but we have done a similar activity. You all know the amount of water that is displaced. If you measure the weight of water that has been displaced, that is equal to the upthrust. So the weight of object in air minus the upthrust will be the reading here. That is the apparent weight. So in this instance, apparent weight is 50 Newton. Here it's 20 Newton. There it is 0 Newton. So those are the information that we know from the activity. The first question. Write the Archimedes Principle. So here write the Archimedes Principle. When an object is partially or fully submerged in a fluid, the upthrust exerted by the fluid is equal to the weight of the fluid displaced by the object. So that is the Archimedes principle. When an object is partially or fully submerged in a fluid, the upthrust exerted by the fluid is equal to the weight of the fluid displaced by the object. So I am sure students, you all know the Archimedes principle by now. You have to remember it and you have to write it correctly. So this is the Archimedes principle. Now we will move on to the rest of the questions there. So the second part of the question, students, write the relationship between the upthrust exerted by water and the weight of the object in the given instances. So in all three instances, what is the weight of the object and the upthrust? In the first instance, upthrust is only, okay. So from these three observations, students, you all can see when we come to this point, that is instance Z. The Newton balance shows a reading of 0 Newton, whereas the weight of the water that has been displaced is 100 Newton. So from that, you all should know that the weight of the object is 100 Newton. Why? Here, there is no apparent weight. So that means the upthrust is equal to the weight of the object. Then 100 Newtons is the weight of the object. So in the first instance, X, weight of the object is 100 Newton, but the reading shows as 50 Newton. So what can you say about the upthrust? Upthrust is 50 Newton. So upthrust is less than the weight of the object. So there, this is what we have to write. In X, upthrust is less than the weight. Then in Y, what happens there? There are also upthrust less than weight. And finally, in Z, upthrust is equal to weight. So those are the relationships there. Then the next one. What is the weight of the object? We have already calculated or we have discussed the weight of the object, that is 100 Newton. What is the upthrust exerted by water in instance X? What is the upthrust? That is 100 Newton. Why? Upthrust is equal to weight. That is when it is completely immersed in water. So you can understand all these calculations. With that, students, we will move on to the next part of the question. Fifth one, indicate the forces acting on the object in instance Z in the given diagram. So here we need to indicate the forces there. What are the forces acting downwards? I will indicate the forces there. Weight is downwards and upthrust is upwards. Or if we draw that and show. So here you can see, students, weight is down, upthrust is up. If we can draw it and show also. So here we have the vessel with water. Object is completely here. So if we the weight and upthrust. So according to the question, we are supposed to mark it in the diagram itself. So here you can see weight is equal to upthrust. So to make it more clear to you all, I have shown it in the diagram here as well. I have not connected the Newton balance or given the values, just to show the forces only. Weight is down and upthrust is up. So then, if we look at the next part, what will happen to the object in instance Z if water was replaced by a liquid of density 2000 kilograms per meter cube? You know the density of water is 1000. So here the density is 2000. So it's more than the density of water. If the liquid is more denser, what will happen to the object? The object here you can see it's completely immersed in water. But then if we put it into a liquid that has higher density, you all know the object will be pushed up further. Why? The upthrust exerted by that liquid with the higher density will be greater. So because of that, to balance that upthrust to the weight of the object will be pushed forward. So the liquid that is displaced will be less. That will be equal to the weight of the liquid that has been displaced will become equal to the weight of the object. So object will be partially submerged and floating in the liquid. So here we can say what will happen to the object. So we will say object will be pushed up so that it will float partially submerged in the fluid. So that is what happens to the object. Then the seventh one. What can you say about the upthrust on the object in the above instance? So there what can we say? What can you say about the upthrust on the object in the above instance? There also the upthrust is equal to the weight of the object. So here we can say upthrust equals weight of the object. Upthrust will be equal to the weight of the object. So I'm sure students you can understand all these questions clearly. And I'm sure you would have also answered them correctly. With that, I will move on to the next question. Extra question 28. A group of students observed Mercury column at different stages as shown below. So here you can see a set of Mercury columns, and in this they have marked all the levels. The levels of Mercury at that height, the vertical height has been marked as 76 centimeter. You can see here the Mercury level. Now the differences can be observed. Here the tube is at this point. Here it is at this point. Here it is right to the bottom. Here of course here, but it is a more broader tube, and there it is a slant or inclined tube. So those are the things that you can see from this diagram. But the vertical height is the same, 76 centimeters. So if we look at the question, what are the students trying to demonstrate? What are they trying to demonstrate? They are trying to show that the pressure exerted by a liquid column depends only on the vertical height, not on the volume of the liquid. Can you all understand that? The shape of the container, of course, is the same. The volume is the difference here. So that is what they are trying to demonstrate. So here we can say pressure exerted by a liquid column depends on the vertical height and not on the volume of the liquid. Second one, what can you conclude from the above observation? The same thing can be concluded. So here pressure exerted by a liquid column depends on the height of the column but not the volume of the liquid. Volume of the liquid. So that is the conclusion that we can get from this activity. Then the next one. Write an equation to calculate the pressure indicated by the above Mercury column. So that of course you know. Pressure equals, there of course the vertical height has been given. We know the equation H rho G. So write an equation to calculate the pressure indicated by the above Mercury column. Pressure is equal to H rho G. That is the equation. We don't have to do the calculation here, students. So I am sure you were also able to answer these correctly. With that, I will move on to the next question. Extra question 29. A group of students took a cubic shaped piece of metal and marked it by a line where its volume was divided into two equal parts. So here you can see that has been done for this cubic metal. Then they hung it on a spring balance and measured its weight in air. So that is here you can see. Thereafter they took a beaker and measured its weight. Then they submerged the metal cube in water to different levels and recorded the spring balance readings and the weight of the beaker together with the displaced water each time as shown below. So again, you are familiar with this activity, students. We have done this in the lab. Initially just above the surface of water. So metal cube near the water surface first instance. Then metal cube half submerged in water. Metal cube completely submerged in water, and the metal cube fully immersed and away from the water surface. So those are the four instances, and here you are given the readings as well. Initially, you can see when metal cube is near the surface, the spring balance reading is 2.4 Newton. So, that is the apparent weight of the object. Now, you all know the terms. Whereas, here you can see weight of the beaker with displaced water is 2.6 Newton. So, here since it is the metal cube near the surface of water, it is the real weight. So, here there is no displaced water. There is no upthrust because it's just above the surface of water. So, the weight given here is the weight of the beaker. In the second instance, where metal cube is half submerged in water, there of course the spring balance reading is less. That is because of the upthrust. So, that is the apparent weight, and here we have the weight of the water that is displaced along with the beaker. Similarly, you can see in the third instance, the reading of spring balance decreases further to 1.2 Newton, and the weight of beaker with water displaced, that is 3.8 Newton. But after it is completely submerged, if it is pushed farther away from the surface of water also, the readings are the same. Spring balance reading is still 1.2 Newton and the weight of beaker with displaced water is still 3.8 Newton. So, you are familiar with these types of observations as well. So, from these students, you know we can calculate the upthrust. So, here you can see 2.6 to 3.2, there is a difference of 0.6 Newton. So, that will be the upthrust. So, in the third instance 3.8 but 2.6 is the weight of the beaker. So, 3.8 minus 2.6, their weight is 1.2 Newton. Here also it is the same, 1.2 Newton. The same way, 2.4, 1.8. So, you have to subtract this, it's 0.6. Again, 2.4 and 1.2, this becomes 1.2, 2.4 and 1.2, 1.2. So, here you can see this is what we have calculated as upthrust. Here we have calculated the weight loss. So, weight loss is equal to upthrust in all the instances. Is that clear to you all? So, with that, I will move on to the questions. Fill in the following table using the readings given. So, here again the stages are given, upthrust and weight of displaced volume of water is given. In the first instance, is there an upthrust? No, because that is the same as having it in air. So, upthrust is 0 and weight of the water displaced is also 0. Metal half submerged, already I calculated it for you all. This was 0.6 and that is also 0.6. Then the next two instances, we calculated it as 1.2, 1.2, 1.2 and 1.2. If you need, we can go back and look at the values. Here you can see initially it is the metal cube near the water surface. So, I told you all there is no upthrust, the object is not immersed in water. So, those are the values. Then, what can you conclude from the above activity? What can you conclude from the above activity? So, from these observations, upthrust and weight 0, 0. 0.6 upthrust, 0.6 weight of water displaced. Upthrust 1.2, weight of water displaced 1.2. Again upthrust 1.2, weight of water displaced 1.2. So, from this, what can you conclude? We can say the upthrust exerted by water is equal to the weight of water displaced by the object. That is how we get the Archimedes principle. This is how we come to understand the Archimedes principle. So, that is the conclusion. What can you conclude from the above activity? The upthrust exerted is equal to the weight of water displaced by the object. So that is the conclusion. The upthrust exerted is equal to the weight of water displaced by the object. So is that clear to you all students? Here you can even say upthrust exerted by water. If you want to be more specific, we can say exerted by water. So that is the conclusion of this activity. I am sure you all were able to write these answers correctly. With that students, I will move on to the next slide. Write the name of the principle related to the above conclusion. So we already discussed that Archimedes Principle. So the name of the principle related to the observation is Archimedes Principle. The next one, write the principle you mentioned above. I am sure by now you all know the principle very well. We have been writing it again and again. What is it? So here, when an object is partially or fully submerged in a liquid, the upthrust exerted by the liquid is equal to the weight of the liquid displaced by the object. So when an object is partially or fully submerged in a liquid, the upthrust exerted by the liquid is equal to the weight of the liquid displaced by the object. So here we can use the term liquid or fluid there. Usually we use the term fluid, even liquid is okay. So that is the Archimedes Principle. With that students, I will move on to the next question. Extra question 30. Two instances that utilize atmospheric pressure are shown in the figure below. So if we look at the figures, you can see the first figure. There is a tank here, another tank there. From one tank to the other tank, water is being transferred. What is that method known as? The siphon method. So then here you can see the next figure where a boy is drinking or person is drinking water using a straw. So there also the atmospheric pressure is used. So we'll look at the questions. Explain how atmospheric pressure helps in figure 2. So figure 2, how does it help? You can remember students, when we suck the air through the straw. So the air enters into our mouth. Because of that, the pressure inside the straw is less. At the same time, the atmospheric pressure is pushing the water down. So with that, the atmospheric pressure here is greater than the pressure inside the straw. The pressure exerted by the air inside the straw. Because of that, it pushes the liquid or water into the straw. That is how it helps to drink water from the straw. So that is the explanation that we need to give. Explain how atmospheric pressure helps in figure 2. So when we suck the air from the straw, the pressure inside is less than the atmospheric pressure. pressure. So, atmospheric pressure pushes the water into the straw. That is how it helps us to drink water, or for that matter any liquid drink. Then what is the name given to the method used in figure 1? Figure 1, I already told you all what is that method. Siphon method. Siphon method. Then explain how water is transferred from tank A to tank B in figure 1. So this is the siphon method. You all know this method, students. What happens here? If we mark this point here, initially there is only water there. What do? We have the tank A at a higher level. We put the rubber tube into the tank. We close the end, this end, and we bring it down. So then what happens is, there it is the atmospheric pressure initially acting at the open end. But here, if you take this point, it is the atmospheric pressure acting there, plus there is a water column. If you take the tube here, there is a height, so there is a pressure exerted by that water column. So if you take the pressure at this point, this end of the tube, it is the pressure, atmospheric pressure, plus the pressure exerted by this water column. So that pressure is greater than the pressure acting here. Why? Because there initially it is only the atmospheric pressure. So when there is an excess pressure inside the water or at this end of the tube, that pressure pushes the water down. So that is how water flows out from tank A into tank B. That is what we need to explain here. So initially, the pressure at the end of the tube in tank A is the sum of atmospheric pressure, and the pressure exerted by the water column above the end of the tube. The pressure at the end of tube in tank B is the atmospheric pressure. The higher pressure at the end of tube in tank A pushes the water through the tube into tank B. So that is the method that is known as siphon method. So if we read the answer again, initially the pressure at the end of the tube in tank A is the sum of atmospheric pressure and the pressure exerted by the water column above the end of the tube. The pressure at the end of the tube in tank B is the atmospheric pressure. So the higher pressure at the end of the tube in tank A pushes the water through the tube through the tube. It should be through the tube. Through the tube into tank B. So that is how we explain this answer or this siphon method. So I am sure students, you would have also explained all these answers clearly and you would have done the calculations properly. So with that students, I have come to the end of this chapter and for that matter, end of this lesson. So under hydrostatic pressure, we discussed the pressure exerted by solids, then liquids and gases. Also the instruments used to measure atmospheric pressure, the uses of atmospheric pressure, transmission of pressure through liquids, and also we discussed the flotation principle, Archimedes principle related to that. So I'm sure you all have a very good understanding about the lesson as well as now you are able to answer many different types of questions.